Let's take another look at an example from section 2. This time let's use the fundamental theorem of calculus to compute the line integral of f dot dr over c for our vector field f of xyz equals z comma y comma x over the helix 2t 3 cosine t 3 sine t, where t runs from pi over 2 to 3 pi. All right, the reason we can get away with doing this is because our vector field cap f is conservative. It's equal to the gradient of a potential function little f. Now, the best way to see that is to actually just attempt to find the function little f that will satisfy the requirements. So we know that the gradient of f has components, the partial of f with respect to x, and so therefore if it's going to be equal to cap f, then the first component must be z. So that means the partial of f with respect to x is z. The partial of f with respect to y is equal to y. And the partial of f with respect to z is equal to x. All right, so now what function f of x, y, z will satisfy these three conditions? Well, if I just take the antiderivative of z with respect to x, thinking z is constant, I just get x times z. And then if I do the same thing with respect to y, I get y squared over 2. Now, if I think about this function, its partial with respect to x is just equal to z. This term will go to 0. Its partial with respect to y is equal to y, because this term will go to 0. And its partial with respect to z, this term goes to 0, and this term would give you x. So in fact, this is a perfectly good potential function to use. And therefore, we verified that the vector field f is equal to the gradient of a scalar function and is therefore conservative. Okay, so in the case of a conservative vector field, so I can replace cap f with the gradient of a function, and then the fundamental theorem of calculus says that this will be equal to f evaluated at the endpoints. So that's r of b minus f of the point r of a. So it says that instead of calculating r prime of t and sort of understanding this curve perfectly, I really just need to plug in the endpoints and see what points in space that I get and evaluate my function f for those coordinates x, y, and z. So for instance, r of pi over 2 is equal to 2 times pi over 2, which is pi, and then 3 cosine pi over 2. Cosine of pi over 2 is 0, and then 3 times sine of pi over 2, which is 3. R of 3 pi is equal to 6 pi in the first coordinate. Cosine of 3 pi is negative 1, so I get negative 3. And sine of 3 pi is equal to 0, so I get 0 right here. Okay, so we know the x, y, and z coordinates of our two endpoints, so we can just plug those in to f. So I get f of 6 pi negative 3, 0, minus f of pi 0, 3. And so what f does is it multiplies the first and third coordinates, so I get 6 pi times 0, and then plus the second coordinate squared over 2. So negative 3 squared over 2, and then minus, and then I get pi times 3, so 3 pi, and then minus 0 squared over 2. Okay, so now we're just simplifying, so we lose this term, and I get 9 over 2 minus 3 pi. And you can go back to the example in section 2 and verify that 9 halves minus 3 pi was exactly the result that we got using the parameterization and just computing this integral in the standard way. So the fundamental theorem of calculus will always agree with the standard method whenever it's applicable. But oftentimes, especially if my curve is complicated, oftentimes it's better to sort of do a little bit of work to find the potential function, and that way instead all we need to know is about the endpoints of the curve instead of what happens in between.